Welcome to our final demo video. Our project is TEX-RAY, textile identification via Raman spectroscopy. Our team members are Ariana Mihandust, PSE, Danielle Samuels, PSE, Austin Frost, CPE, and Cameron Ricketts, EE.
Our project TEX-RAY utilizes Raman spectroscopy to acquire the Raman fingerprint of a textile sample and sort the sample as being cotton or polyester. This will enable users to verify the fabric composition of their clothing items. It also enables a product comparison feature, in which users can store and keep track of the spectral signature of their authentic items. This allows for verification of authenticity of any replacements or second copies purchased of their database items.
This chart details all of our important engineering requirements. The highlighted rows are the demonstratable requirements that we will explore in this demonstration. The system should be able to identify a textile sample with 90% accuracy. The user should receive a readout result within 15 seconds of initiating analysis, and the system should also be able to compare the composition of different products with 90% accuracy. Here's an assembly view of TEX-RAY. The overhead compartment will hold all the optical components, while the lower compartment will hold the PCBs and the power supply. An acrylic square covered with black vinyl acts as a base for the optical components, allowing for ventilation for the PCBs underneath while still keeping the optics in the dark. A spray-painted black acrylic square acts as the lid for the optics, enclosing them.
Here's a closer look at our system. To initiate operation, the user would first place their sample inside the sample holder and then place it back into position as shown. They would then select either material analysis or product comparison mode on the LCD screen, initiating laser turn on. Here's a look at the probe optics inside of our system. The 532 nanometer laser will be focused onto the beam expander via kinematic mirrors for the purposes of alignment. The expanded beam will be redirected by the dichroic mirror onto the sample, upon which Raman scattering will pass back to the dichroic mirror and through the long-pass filter for isolation. The Raman signal will then be coupled into the spectrometer portion.
The Raman signal coupled onto the slit will diverge through it spatially filtered. We then recollimate the light with a 50mm achromatic lens. Then this collimated beam will be incident onto the reflective diffraction grating at a 0-degree angle of incidence. The different wavelengths of the Raman scattered light will be diffracted at different angles by the grating, and then be focused onto the detector by another 50mm achromatic lens.
Here I'm testing my voltage regulator. This is a 12 volt regulator with a 9 volt input. Here we can see we're getting 12 volts at the output from the 9 volt source. Now when I draw 0.5 amps from it, we can see it's still regulating about 12 volts, showing that it works. Here I'm testing my 3.3 volt regulator. We have a 9 volt input and we're getting 3.3 volts out. And then when I draw the current from it at 0.5 amps, we're still getting 3 volts. Here we are testing the 5.4 volt regulator. We have it hooked up to the power supply. That will be the input. And then we have it hooked up to the electronic load. And we can see we're getting 5.4 volts out. When we draw the current on the electronic load, it drops, but we can still see we get 5.4 volts out. Here we have the power supply feeding into the main board, which is powering the 3 voltage regulators, the 5 volt, the 3.3 volt, and the 12 volt. The 12 volt feeds into the laser. It is being controlled by the ESP32. Here we have the Raspberry Pi connection, which is receiving power from the 5 volt regulator. The LCD is connected to the Raspberry Pi directly. And we also have a direct connection from the Raspberry Pi to the STM32 via USB-C. And we have the CCD in here, which is giving us this waveform. Here we'll be testing our signal amplification board as the input signal flows through the op-amp and through a low-pass filter. Here we have the DC inputs. Here we have the input signal at 150 millivolts peak to peak, and the goal is to have a gain of 10 at the output. Firstly, we'll take a look at the waveform generated by the input signal, and we can see that it goes from negative 150 millivolts to 150 millivolts. We will now display the output signal and see how it compares to the input signal. It can be seen that the reference voltage is at about 1.65 volts, and the output signal is going between 0 volts and about 3.3 volts. A reduction in noise can also be seen, making this test a success.
While the CCD sensor is operating correctly from the current STM32 code, and the comparison algorithm has produced results of 100% accuracy across recent trials, our physical system as it stands is not operational. This is because of an issue related to the direct memory access being used to send the converted digital data from the STM32 to the Raspberry Pi. The code is written to take the markers added to the beginning and end of each data frame and use them to display only singular frames of data on the LCD, and in doing so use these individual frames to demonstrate the comparison algorithm. However, a timing issue has the DMA writing into the buffer as it's being sampled, resulting in corrupted data in each frame to the point where the data being sent from the STM is not usable, and thus the system overall is not currently functional.
This first demonstration of TEX-RAY shows the operability of our integrated system, meaning the performance of the probe optics coupled to the spectrometer optics. We tested the integrity of our Raman system using a Thorlab CMOS detector. We firstly calibrated our system with a fluorescent bulb. We then took and processed an image of Raman scattered light from acetone. The peak found at 552 nanometers aligns with the references we've seen in literature. Since the resultant images of the spectrum were taken with the Thorlab CMOS camera and not our intended detector, this only gives an approximate sense of the performance of the system as a whole. However, this verifies our system's ability to produce, collect, and identify a Raman signal. We then proceeded to take the following photos of the Raman scattered light from polyester and cotton. We suppressed the power of the incident light onto the sample with a neutral density filter and saw more defined peaks. Then, as you could see without the filter, more power resulted in broader peaks, which we correspond to more emitted fluorescence from our fabric samples. This pattern is also seen when using a commercial spectrometer. Despite fluorescence, our main concern still is differentiability between the two spectra, which we will assess more in the next functionality test of our system.
Because our STM is not outputting data as intended, and to further prove the robustness of our optical system, we will be conducting the material analysis and product comparison tests via the StellarNet Blue Wave miniature spectrometer and coupling our Raman signal into the spectrometer fiber for viewing. Before getting into the material analysis tests, let's quickly review the key Raman peaks of cotton and polyester. One of the largest differentiating factors between these fabrics is the fact that polyester has prominent peaks at 1600 and 1700 wave numbers, whereas cotton does not. This will be a key factor in their identification. Let's begin with the material analysis testing, starting with polyester trial 1. Here we can see that we have an integration time of 10 seconds and that the signal is flattened, meaning there is no sample present. Next, we will place the polyester sample in its location. After placing the sample and waiting the 10-second integration time, a spectrum forms, with a clear peak at 586 nanometers, corresponding to 1700 wave numbers, characteristic of polyester. For trial 2, we will remove the sample and then place it back to see if the same spectrum forms. Again, we let the spectrum zero out before placing the sample, then wait the 10-second integration time to view the spectrum. We once again see a peak form at the same characteristic location. We follow the same procedure for trial 3 and again see the same results. 10 trials each for both cotton and polyester were conducted in this manner.
Here we have the Python code running the sorting algorithm against 10 trials of polyester and 10 trials of cotton. Being shown right now are the cotton and polyester datasets for each trial after running through a Savitsky-Golay filter. And this is the results of what's actually being compared after going through a smoothing algorithm. And below you show the dynamic time warping results with each trial showing the most similar comparative trials, the lower values representing more similar trials.
Now let's move on to product comparison testing.
To test the product comparison feature, which should theoretically be able to spectrally differentiate dupes from authentic clothes, we tested two visually identical black t-shirts made of different materials. Again, using a 10-second integration time, we follow the same procedure as shown in the material analysis testing, where we place the sample, allow the 10-second integration time to run, and then view the resulting spectrum. Again, these tests were conducted across 10 trials for each shirt.
Here we have the results of the same noise filtering system, in this case for two distinct shirts, with these results coming from the first and these from the second shirt. And once we scroll down, we'll show what's actually being compared after polynomial fitting is used, with the blue and orange being polyester and the red and green being from two cotton trials. Here we show the results of the sorting algorithm, with 10 polyester trials and 10 cotton on the left to showcase the material sorting accuracy. There with 180 potential sorts across 4 different types of k-nearest neighbors, with 3, 5, 7, and 9. The resulting comparison is right 173 out of 180 trials, showing 96% accuracy. On the right, we have the product comparison, in which 175 correct trials resulted from 180. This was taken across trials with 10 results of a t-shirt and 10 of a jacket, again with the k-nearest neighbors of 3, 5, 7, and 9 for each trial.
After analyzing all of our subsystems separately, this is where we stand in regards to our engineering requirements. Our material analysis accuracy and product comparison accuracy perform well after comparing trials across multiple days. Our total response time was estimated by considering our spectrometer integration time and software runtime, and came out to be approximately 10 seconds, which is on target.
Thank you to Chroma for generously lending us a dichroic mirror and long pass filter, and to Test Fabrics Inc. for providing us with industry standard fabric samples. This has been our project, TEX-RAY.